let's start right now with the first presentation. So, Professor Idol from the University of New Mexico, distinguished professor. It was formally presented yesterday, and let's welcome with applause, please.
Thank you.
Yeah. Professor Ido, the floor is all yours.
Thank you. Thank you. Good morning, everyone. Thank you for getting up so early to listen to us. I work on lots of projects. I have selected two that I would like to share with you this morning. So the first one is on the NSF IRVA. And, okay, you're going to turn. So in 2020, NSF launched a call for proposals for a program they called the Engineering Research Visioning Alliance. And in January of 2020, just when the pandemic hit, I was contacted by a gentleman from UIDP. UIDP is University Industry Demonstrations Project. It is an organization, it's a nonprofit organization that started with the National Academy of Engineering, and about 10 years ago spun out of the National Academy of Engineering as a separate organization. The purpose of that organization is to bring universities and industries closer together. He contacted me and explained that he's part of a team, and would I like to join that team as a co-PI? So I did, and it was a very interesting process because I didn't know any of the co-PIs. Only a couple of them knew one another, and we worked during COVID. So actually we worked 5 days a week on Zoom from February till August to put this proposal together. We submitted the proposal in August, and then we found out in November that we were selected, and the program started in April 2021. Okay, so next slide. So the PI is Dorota Grezner-Brzezinska, who's with the Ohio State University. She's actually moving to the University of Wisconsin as vice president for research. Anthony Boconfuso is a co-PI, and he's the gentleman from UIDP that had contacted me and pulled me into this. Charles Johnson Bay is the industry at large member. He's with Booz Allen Hamilton. Pramod Karganikar is a replacement co-PI. Our original co-PI representing universities at large went back to NSF, so he couldn't serve as co-PI. So we invited Pramod to join us. Pramod is a former director of the engineering directorate at NSF, and then it's me. Thanks. So what's the idea about IRVA? So NSF wanted an entity to help, not just to help NSF, but to help the entire engineering research community, meaning federal agencies, academia, industry, to identify nascent areas of engineering research where some modest investment can lead to big payback. So in other words, NSF wants us to look under rocks. They want us to look around the corner. They want us to help identify research themes that no one else is thinking about. Believe me, it's a very hard problem. It's not easy, but I'll explain to you what we're trying to do. Next. So there are three core partners. So Dorota, who's with the Ohio State University, Ohio State is part of the Big Ten Academic Alliance. So she represents the Big Ten Academic Alliance, which are the large universities in the Midwest in the US. I was selected because I'm in New Mexico, and New Mexico is an EPSCoR state. What that means is NSF ranks every state in the United States and ranks them with how much money they receive. As you can imagine, the states that receive the most money are like California, Massachusetts, New York, Texas, the big states. So NSF ranks all 50 states and then draws a line. And those that receive less money than at the top, they're part of the EPSCoR jurisdiction. So New Mexico is an EPSCoR state, and so they wanted a co-PI from an EPSCoR state, so that's how I got involved. And then Tony represents a UIDP. UIDP is actually the organization that receives the dollars. So Dorota with Ohio State is the PI, but Ohio State receives the money as a subaward from UIDP. Next, please. So we have affiliate partners. These are entities that don't receive money from us, but they support us and work with us. So you can see it's a good number of, organizations, many which are quite prominent. Next, please. Okay, let's click this. So between the co-PIs, the advisory, so the structure of IRVA is we have the PI, co-PI team. Then we have, at the highest level, the advisory board. The advisory board consists of about 10 individuals, and these are very high-level people. As an example, the president of University of Maryland, Darrell Pines, is a member of the advisory board. Kim Budil, who is the director of Lawrence Livermore National Lab, she was on the advisory board. So the advisory board is the very highest level, about 10 individuals. Then we have a standing council, which has about 35 individuals. The standing council is the brain trust, so let's click again. And the standing council is the body that vets the ideas that come to us. So we as IRVA accept ideas from everybody all over the world. Anyone can submit an idea to IRVA. The first body that filters the idea is the standing council. So these are all prominent engineers from all over, from national labs, from academia, from industry. Next, please, one more. And then the thematic task force is the following. So what does IRVA do? So 4 times a year, we organize a brainstorming event. We call it a visioning event. So once we select the topic, we organize a visioning event, and then we organize a thematic task force. A thematic task force comprises about a dozen individuals. They are the technical subject matter experts on the topic, and they're the ones who organize the visioning event. Then the visioning event happens. It's a 2-day event where people come from all over the country, or we do it virtually, and they have multiple sessions where they come up with ideas. Then what we're supposed to do is, within 100 days of the visioning event, we write a report. And then we disseminate that report to everybody, to the government, to agencies, to academia, to industry, with the hope that someone will pick up on that report and say, oh, this is a good idea, let's put money into it and start a program in this area. So that's what we're all about. So you can see here, let's go one more. So between all these organizations, we cover the vast majority of the states in the United States and the 3 territories associated. So, NSF wants impossible things. NSF at the same time would like to see MIT and Stanford in the room, but then at the same time, NSF says, well, why isn't, Texas agriculture and technology in the room? They want everything. They want the elites. They want the lowest level institutions. They want experts. They want junior faculty. They want diversity all across the board. So it's really an impossible problem. Next, please. And with UIDP, we've covered all 50 states. Next. So as I mentioned, the first step is we have an open call for ideas. Anyone can submit an idea. A student, faculty, industry, a government person, somebody from Brazil, anyone can submit an idea. Once we get that idea, it goes through our process of vetting through the Standing Council. We then rack these ideas, we prioritize them, and then we say, okay, next year we're going to have 4 visioning events. It's going to be these 4 topics. Idea is selected, it goes to a visioning event. 100 days after a visioning event, we have a report. Hopefully, it's a high-impact report, and then we disseminate broadly. We've held events at Congress where we talk to staffers, we explain to them what we're doing, we give them the reports, and hopefully they will run with it. Next, please. So to date, we've executed 10 visioning events, and you can see the very, very first one was the role of engineering in addressing climate change. So you may ask, well, why did you pick that as the first idea? So our first open call for ideas was in August of 2021. And so we had an open call for ideas, and the vast majority of ideas that we received had to do with climate change. Well, it just so happened that the week before our open call, the Interagency Panel on Climate Change had released their most recent report on climate change. So because of that publicity, I think that's why that caught the attention. Our second event was leveraging biology to power engineering impact. That idea came from Susan Margulies, and Susan Margulies is a bioengineering professor from Georgia Tech, but she's also the head of engineering today at NSF. So she gave us that idea. Then we had an event at MIT, Engineering R&D Solutions for Unhackable Infrastructure. We had an event on sustainable transportation networks. We had an event on engineered systems for water security, engineering the future of distributed manufacturing, engineering materials for a sustainable future, strategic thinking for engineering research in the era of artificial intelligence, engineering solutions to combat antimicrobial resistance, and quantum-enabled technologies. So as we have these events, we're learning, we're maturing, we're getting better. And one thing we instituted last year is each PI, so there are 5 of us who are co-PIs, each one of us picks one of these events and we're responsible for it. So I was selected to be responsible for the quantum-enabled technologies, so I'm on the hook for writing the report because I couldn't find anyone to write the report, so I'm going to do it. And for the AI report, Pramod Garganikar couldn't find anyone to write the report, so he wrote the report. So the next thing I need to do is get that report out. Next, please. Here are QR codes for the published reports. Our website is irvacommunity.org. All our reports are available there. You're free to download it and share it. And again, we're looking for ideas, and we're asking everybody for ideas. Next, please. So we have 2 upcoming events. The next one, which is generating a lot of buzz in June, is Transforming Women's Health Outcomes Through Engineering. This is very good timing because the White House got attention of this, and the White House has been thinking about women's healthcare. I mean, there's a lot of disparity in healthcare between men and women. In fact, there are a lot of bias in healthcare towards men, and not totally accounting for differences in women's health. So this event will be held in Columbus, Ohio, and the idea is how can engineering help level the playing field in healthcare between men and women. And then in June 13th in Denver, Strategic Engineering for Next Generation Wireless Competitiveness. So what that is all about is the fact that the US has fallen behind in terms of wireless technology. We've fallen behind to Japan, to Finland, and other European countries. And the idea is how can the United States leapfrog and come back to a leadership position in wireless technologies. Next. So here are some signs of impact. We had an event on Capitol Hill in Congress after our first event, and we were able to have my Congresswoman, Melanie Stansbury from New Mexico. She and her staffers hosted an event, and we distributed the reports. And you can read the rest, but basically, it's IRVA is you know, we're fairly new. We're 3 years into it. We're now in our 4th year. It takes time to build a brand name. It takes time for people to know who you are, and you know, it takes time. So we're all working very hard, and we're hoping that more and more people will become familiar with it. This is why I'm bringing it to your attention, because it is an opportunity for engineers in Brazil to suggest ideas and allow us to make an impact. Next, please. So, again, we want to share our reports broadly to anyone who's interested in the future of engineering research. Again, our website is irvacommunity.org. Use our reports. If our reports can impact how you think about research in engineering, let us know. Engage in our events, nominate speakers, nominate participants. We have a budget to pay for travel for participants to come to our events. And again, share your visioning ideas. So that QR code on the bottom right is the form where you can submit an idea that you think that no one else is thinking about, that is that can be potentially very impactful in engineering. Next. And with that, I'll stop here. So let me go on. I have a second presentation, and that is on our different topic, but you know, yeah. Okay, that's, yep. So in 2021, so my research, I'm a plasma physicist. So my PhD in graduate student was plasma physics for fusion energy. And the technology I used was pulse power technology to generate proton beams, and using proton beams to generate field reversed ion rings to confine a plasma. I was supposed to go to Los Alamos as a postdoc when I graduated in 1988, but in 1987, President Reagan eliminated alternate concepts fusion and said the United States will only spend money on tokamaks. So tokamaks are the big donuts that are used to confine plasmas. Well, my postdoc went away. I was out of a job and just waiting to graduate. And then I get a phone call from the University of New Mexico. Stan Humphreys calls me, and he invites me to give a talk. I thought he was looking for a postdoc. Turned out to be a faculty position, so we came and we stayed. So usually when you're an assistant professor, you do research in the topic you worked on for your PhD. Well, I couldn't do that because there was no money in alternate concepts fusion. But the technology that I knew pulse power technology, I knew how to make proton beams, and there were two professors at Cornell who worked on high power microwaves, John Nation and Chuck Wharton. They were the founders of high power microwaves in the United States. So what high power microwaves is using pulse power technology to generate electron beams. Remember, I knew how to make proton beams, but making electron beams is easier. You just have to change the polarity of your pulse power machine, and then you make an electron beam. And then what you do is you take energy from your electron beam and you convert it to microwaves. That is the bottom line. So pulse power was invented, modern pulse power was invented in the 1960s in the United Kingdom, and it was actually invented by a group at the Atomic Weapon Research Establishment that wanted to make more X-rays to study dense implosions. So Atomic Weapons Research Establishment in the UK is like the combination of Los Alamos and Sandia in the United States. They make nuclear weapons. And to study it, they need to make X-rays of the imploding object. Well, it turns out that commercial X-ray machines did not have the fluence to penetrate the dense matter. So the group at AWRE learned how to make more X-rays by inventing pulse power. So what pulse power is, prior to pulse power, you can make electron beams with a megavolt energy, a million volt energy, but only 1 or 2 amperes of current. What pulse power allows you to do is make a megavolt electron beam, but instead of 1 ampere, you make 10,000 amperes. So that's the technology. And John Nation at Cornell was a plasma physicist, and he did the math. He said, okay, if I have 1 megavolt beam with 10 kiloamps of technology, that's 10 gigawatts of beam power. And if I can only convert 10% of that to microwave, that gives me a gigawatt. And that's huge. Back then, no one knew how to make a gigawatt. People made at most a few megawatts of microwaves. So that's how this field started. So in 2021, we founded, let's go next. So we founded the Directed Energy Center at UNM through support from Congress. And these are the key players. Next, please. So we have an advisory board. Our advisory board consists of researchers at AFRL, folks in industry, and these are this is the group of people that gives us guidance as we move forward with our center. Next, please. So BLUF stands for bottom line up front. So this is an exciting time for directed energy. So what is directed energy? Directed energy is making either very high power of microwaves or very high power of lasers. And why is the Air Force Research Lab in Albuquerque is the center of directed energy for the Air Force, but also for the DoD. Among the DoD services between the Navy, the Army, the Air Force, and others, the Air Force is the nation's lead in directed energy. So what directed energy allows you to do is, for example, if you use kinetic munitions like bullets or missiles, they travel relatively slow. Directed energy travels at the speed of light. So you have speed of light engagement, and potentially you have infinite magazine, meaning you won't run out of bullets. You can keep firing, and the cost of each individual firing is minimal. Next, please. So just to put it in perspective, the budget in the United States for directed energy is $1 billion annually. And the Air Force Research Lab budget is a third of that. So Air Force Research Lab has $300 million. I would estimate half of the DoD's investment in directed energy is in New Mexico, between the $300 million at AFRL, Sandia, Los Alamos gets funding, and numerous industry get funding as well. So I would say about half of the DoD investment is in New Mexico. And UNM, my university, is the only university in the US that has a research and education program in both lasers and microwaves. Next, please. Okay, so why is directed energy so important? So you may remember last fall, October, November, December, the United States Navy was struggling to keep the Straits of Hormuz and the Red Sea open for international shipping because the Houthis in Yemen were firing drones and missiles and all that. And for those 3 months, the United States Navy spent $1 billion. $1 billion in 3 months. That's the entire budget, annual budget in directed energy. And how was the US defending against these attacks? They were using missiles and munitions where the cheapest missile costs $25,000 and the more precise targeted missiles are several $1 million each. So you're firing $1 million missiles against targets that maybe cost $1,000. So that's a lot of asymmetry. So there needs to be another solution. Next, please. So on the right is an example of a high-power microwave system that was developed at Air Force Research Lab. That looks big, and I can tell you it doesn't have to be that big. It's only that big because the Air Force had 1.5 years to develop that prototype, and that container is only about a third filled with things. It just happened to be available, and they used it, so it's not that big. I had 2 of my former PhD students were the technical leads on that project. So that's called Thor. It's tactical, high-power operational responder. And that device was demonstrated to take down an entire swarm of drones. They did tests at White Sands in New Mexico, and they were able to successfully defeat drones. And on the left is a directed energy laser from Boeing. The advantage that microwave has is the microwave beam is a very broad beam. So you can take down a swarm just by doing this, whereas if you're using lasers, you have to quickly track, point, shoot, and move, and it's a harder problem with lasers. Next, please. I just have a couple of slides on the laser work. So UNM does work on fiber lasers and diode lasers. UNM holds the world's record on cooling in fiber lasers. Next, please. And that's the evidence of the cooling. That's a world record delta T, and this is in collaboration with Fraunhofer Institute in Germany. Next, please. Okay, so talking about microwaves, where does the directed energy microwave world sit? So we're looking at a plot of peak power versus frequency. Notice the red dashed line on the bottom left. That red dashed line represents the maximum of what solid-state microwave devices can do. So solid-state microwave devices will never be able to go to the very high power levels. And the reason is simple. Electrons in solid-state microwave amplifiers, electrons drift in a medium, okay? Whereas in high-power microwave sources, electrons move in a vacuum. Because they move in a vacuum, there's no resistance, there's no heat dissipation. So solid-state devices will always have a thermal problem as they get to higher and higher power levels. And you can see where in the blue is where radars sit, and in the green is the microwave sources for RF accelerators. So the high power world is there. It's low duty cycle. In other words, you can't fire 1,000 shots a second. You can fire perhaps 10 shots a second, but you make very, very high powers, like gigawatts, multiple gigawatts. But the pulses are short. Pulses are tens of nanoseconds. So the energy content is insignificant. To put it in perspective, if you want to boil a cup of water in a microwave oven, if your microwave oven is 1,000 watts, it takes about 3 minutes to boil water in a microwave oven. So 3 minutes, if you do the math, 1,000 kilowatts, 3 minutes, that's 60 seconds times 3 times. You're going to need tens of thousands of joules of energy, tens of thousands of joules. Each of the microwave pulses we generate is only about 10 joules. So there's no energy content in the microwaves. But what's important is that the power levels are very high. We're talking about gigawatt plus power. And as you know, electric field is the square root of power. So if you have high power, you have high electric field. And it's that high electric field that couples into systems and can disrupt the electronics. Next, please. So the landscape in directed energy is shifting. It used to be that the basic research focused on low frequency, on like 1 gigahertz, 2 gigahertz region, because that's the frequency that's used for counter electronics. But ever since this report came out, the DoD is now shifting. So now the DoD is interested in high frequency. So we used to play in the 1 to 2 gigahertz range. Now we're told to shift to X band to Ka band. So 8 gigahertz to 42 gigahertz. So we're now retooling and investigating how to efficiently make sources at higher frequency. Next, please. So some of the technical work that we're doing is, one important project is we're researching a multi-beam traveling wave. So traveling wave tubes have been around since the late 1930s. In fact, the Voyager spacecraft that was launched in the early 70s that has left the solar system has a traveling wave tube on it that's still sending information back to Earth, and we're still able to, so that's amazing that such a device is still working after these many decades of operation. So long story short, we're learning how to make a traveling wave tube at very high power levels and using 2 beams instead of 1. And if you use 2 electron beams, you can make microwaves more efficiently. Next, please. We've had 3 books on the topic of high power microwaves. Next, please. And so others associated with my center are, we have an assistant professor at UNM, Victoria Babacheva, and she's using the funding to learn how to make higher energy density capacitors. Next, please. We have a small business. One of my former PhD students, Sarita Prasad, is studying how to phase lock high power microwave sources. Next. And we have COSMIAC. So COSMIAC is a School of Engineering research center at the University of New Mexico. Christos is the director of COSMIAC. And COSMIAC is special because, first of all, it's not on main campus. It's located near the airport, south of campus. And one of COSMIAC's mission is to get undergraduates and graduate students, get them cleared, in other words, get them a security clearance so that once they graduate, they're ready to go and work at the Air Force Lab, at Sandia, at Los Alamos, or in industry. There's a tremendous lack of workforce in the United States, particularly US citizen workforce. The labs and industry need US citizen trained engineers, and there's a shortage of those. So we're working hard to develop the workforce. Next, please. We also have academic curricula in lasers that resides with the Optical Sciences and Engineering program, which is a joint program between electrical computer engineering and physics. And then the high power microwave program is in applied electromagnetics, which is the group that Christos and I are part of. Next. Also, since spring of 2017, I started a online course called Introduction to Directed Energy. It's 8 weeks, all online, and it's intended for the non-technical person. So it's intended for people who work either at the labs or work in acquisition for the government, who know nothing about the technology, who want to learn about it. So that's a course that I teach. Next. And the next round will be from August to October this coming fall. Next. There's also a lot of synergy with EPSCoR. I mentioned that UNM, University of New Mexico, is in New Mexico, which is an EPSCoR state. So we have an EPSCoR office, and my co-director, my associate director of the center is Gunny Balakrishnan, and Gunny is the director of New Mexico EPSCoR. So what that means is he has an office and a staff that can help us. So the Air Force Research Lab, when we got this money, said, we don't want you to just do research and write papers. We want you to build a directed energy ecosystem from New Mexico down to El Paso, so along the Rio Grande corridor, because so what that means is they want us to support faculty at other universities in New Mexico and West Texas that don't do research in this area to get them involved. And they want us to do outreach. So in Albuquerque, we have a very nice museum for children called Explora. It's a science museum, and we're working with Explora to have an exhibition on directed energy such that students from kindergarten through high school will learn about it and then maybe want to continue studying it. So we, we're tasked with building, changing and building the culture in New Mexico, because this is such an important technology in New Mexico. Next. And of course, that's our senator, one of our 2 senators, Martin Heinrich. Martin Heinrich got his master's in mechanical engineering at UNM. In fact, he's one of a handful of senators that are engineers too. Okay, he's one of 2 senators that is an engineer. And he, in fact, worked in directed energy. He was a contractor working on base at Air Force Research Lab on high power microwaves with Fiori Industries. So he then left, became a city councilman in Albuquerque, then he became our congressman, and then he became our senator. So he's very supportive of this technology, and it's because of his support that we were able to get this additional funding. And with that, I close my presentation, and I'll be happy to take any questions.
People here from Brazil, what would be the best way? I know you showed a lot of information, but now that they know you, they have your email, it'd be easier if they send you an email about ideas.
For IRVA?
Yes, and also you have a budget that can fly.
That's right. So you can send me ideas, or you can go to the IRVA website, irvacommunity.org, and there's a link to a form where you can submit your idea on a future topic of visioning.
One about IRVA. Then we enter the subscription.
So if you go to the IRVA website, you can sign up as a champion. So there's a link that says become a champion. And if you sign up as a champion, you'll get our emails and you'll get our reports.
How we deal with the patent issue,
For IRVA?
Yeah.
I think what we're dealing with is so early, so nascent that it is development, pre-patent. I think once you have a visioning event and you have a report, and if a program gets funded, then I think there's opportunity to develop something that might be patentable. But I think this is very, very early stage. Ugo.
What you mentioned, you also work with high power laser.
Yes.
You use fiber lasers sources?
Yes. So they do. We used to have a fiber draw tower. We don't right now, but we're planning on acquiring another one. They collaborate with Germany, and Germany develops the fiber for them. So yes, so it's fiber lasers and then developing diode lasers as pumps for the fiber lasers. I do not know. I'm not the laser guy, so I don't know. I haven't heard that name come up. So yeah. Mm-hmm. Mm-hmm. Yeah. So NLTLs, I think there's lots of interest in NLTLs, and I think the Romanchenko's group has gotten as high as 10 gigahertz with magnetic NLTLs. I think it's just that the sponsors now in the DoD are no longer funding universities to do basic research at low frequency, because I think the sponsors feel that the technology has matured and they're already building prototypes and systems. They want the basic researchers, they want academia now to shift to look at higher frequencies, 8 to 42 gigahertz, because of course our near peer competitor is China. China is investing a lot of research, a lot of resources in this technology. So United States cannot compete with China in numbers. So we have to be very careful and selective and thoughtful. Yes, Tanya. No, there are non-defense applications of the technology. Of course, the same technology is also exactly the technology that's used in particle accelerators for medical applications. It's used for power beaming. In other words, there are dreams of having orbiting satellites with solar collectors and then taking the electricity that's collected in orbit and then sending it to Earth. How do you send it to Earth? Microwaves. So there are other applications, but the applications that I'm funded for are from the Air Force. So.
Sorry to interrupt. We have to go on next talk. Professor José Rossi, please.
Good morning. It's very nice to be here. Thanks for the invitation, for the participation in the workshop on education, society, and technology. I'm the principal investigator, Dr. José Rossi from Unicamp in São José dos Campos, São Paulo, Brazil. Okay, and the title of my presentation will be radio frequency generation using nonlinear transmission lines at the National Institute for Space Research. Please, next slide. Here is the summary of my presentation. I'll give you a project timeline, the research background and motivation. Then we pass to, I'll talk more specifically about my research, which is on NLTLs, which like lamp lines. We'll give you the results, experiment, spy simulations. We also talk about gyromagnetic lines, results, giving the experiment simulation using numerical codes or electromagnetic 3D-dimension softwares. And in the end, the final considerations, my final considerations. Please, next slide. Okay, before moving to the research specifically, I'll give you some idea where is INPE and the research activities of the Institute. The main INPE's main achievement is the CBERS 4 and the Amazonian 1, launched recently. INPE is in São Paulo State. INPE is involved in environmental remote sensing, forecasts, weather forecasts. There are many areas in the Institute. Here is the plasma laboratory site where the research is conducted. And this is a view of our city, São José dos Campos. Please, next slide. Okay, this is only to give you an idea of the research areas of Plasma Lab at INPE. We have also material surface, research on material surface treatment by plasma processing, research on magnetized plasmas. We are also building an electrostatic energy analyzer for a scientific satellite called ECORS mission. Also, we have the research on the talk topic that we're discussing now, nonlinear transmission lines for RF generation. Please, next slide. Okay, this is a timeline of the project, considering the fundings. We started in 2009 with the first funding from AFSR, SWORD, from the SWORD office in Chile. We've got a second one from 2013 to 2014, another one in sequence from 2014 to December 2015. The last one was this from 2017 to 2020. Also, we had a funding from FAPESP from 2019 to 2021. And we have a lot of money spent on this project. Please, next slide. Okay, now is the present project status of the research. From 2009 to 2024, certainly we had more than 100 publications, considered periodicals, conference proceedings, and master and doctorate thesis. Last year, under the project, we got one master thesis on BSCT, ceramic samples, nonlinear ceramics, and one doctoral thesis on numerical simulations on gyromagnetic lines. I'm the PI, of course, I told you before, and my co-PI, Professor Ido Shamiloglu from UNM, to help us. We have two people from INPE's staff, one master researcher and one collaborator. We have one postdoc collaborator with CNPq fellowship, Fernanda. We will have one engineer in July. He's about to join our group, also with the CNPq fellowship. And we have established collaboration with Unifesp, Professor Lauro Silva, and UNM, Professor Ido Shamiloglu. And we have a proposal for a new AFOSR sword funding. This is the title of the project, the development of a compact bench gyromagnetic NLTL for space applications. And unfortunately, this is on hold because INPE now is requiring hard paperwork that requires an agreement between INPE and Feec to receive the funding. But we need more 1 month still to get the agreement done and to open the bank account to receive the funding. Please, next slide. These are the recent publications of our past input pulse with a rise time of 2 or 3 nanoseconds. You create azimuthal field, HV, and you have, of course, the line is immersed previously in a bias magnetic field generated by a solenoid. Then you have that figure here. When the positive current comes, you create the HV field that interacts with the bias fields HZ. And this effective field is formed, and then M is the magnetization of the ferrites. It presses around the effective magnetic field, inducing oscillations along the line. And these lines appear at the output pulse on the pulse amplitude at the output. And these oscillations are the RF that we're generating. But of course, we need to remove the DC component to feed an antenna. Okay. Please, next slide. Okay, here it is the operation frequency range for at the present status of both lines. With lamp lines, we start from 5 megahertz to 1 gigahertz. For lamp lines, it's very hard to overcome 1 gigahertz. But for gyromagnetic lines, we can reach up to 5 gigahertz. And with gyromagnetic lines, we can get power, high power. With lamp lines, you can reach maybe 800 megahertz, close to 1 gigahertz, but with low power, with only using low varactor diodes. Okay. Okay, because it's not working?
Not working, sorry.
Okay. But here it's this figure here. You have the precession movement of the magnetization of the ferrite. Okay, precessing around the effective H field, and here's the the LC component using the section of a transmission line. Please, next slide. Okay, the main applications, we have several applications, maybe as ultra-wideband pulse radar in the transmitting system, basically, because you are generating the 2 gigahertz as the carrier wave signal. You have also used, as Ido told before, disruption in communications, in defense. Maybe we can use as RF source in space vehicles, and maybe we will have applications in synthetic aperture radar for remote sensing. Basically in P-band, L-band. P-band is about 450 until 450 megahertz, and the L-band between 1 to 2 gigahertz, but we are using gyromagnetic lines. For P-bands, you use maybe lambda lines. Please, next. Okay, other applications could be also in communication systems of CubeSats, as they can operate in the UHF range, or maybe in drones. But maybe in drones, 124 megahertz, in this case, maybe it's possible to use LC lambda lines. But other application for gyromagnetic line in defense is to be shooting down drones, okay? Because when you spread a high frequency burst in the air or in the space to shoot down the drone. Please, next slide. Okay, here we've got some results from nonlinear transmission lines. We started using the initial project using 6 sections, using varactor diodes, SVC236, with linear 100 nanohenry inductors. We made this project, but we needed to build the line in a straight line, because if you start to do some curves or quadrants, it's not good because of the parasitic impedances in the PCB structure. Also, in this experiment, we use a pulse generator with an amplifier, the NLTL, and to see the signal on the scope, we use a 30 dB attenuator, because you can burn to avoid burning the input of the scope. And okay, here is the photo for the experiment. Okay, showing pulse generator, the amplifier power supply, and so on. Please, next slide. Okay, here is the measurement on 50 ohms load, which is the input channel of the scope. And here we got in green the input signal. It's kind of a Gaussian pulse shape. And we got a a good agreement between simulation in LT SPICE, which is in red, and the experiment in blue. There is a good agreement because you see this is the output with the oscillations. We've got 230 megahertz in this. This is the fast Fourier transform, the spectrum frequency, with the peak means that we got the oscillations around this frequency. Okay. I think it's about 300 megahertz. Okay, 300 megahertz. Okay, next slide. We have done also measurements on a pulse repetition rate. Also, we got only it's possible with the simulation in red in each space because there is a good agreement. The curves are on each other. And we have an expanded scale in time showing the several pulses. Okay, please next slide. Okay, but to feed the antenna, you need to remove the DC component because the antenna needs only the oscillations without the DC level. We design a high pass filter, and this is the insertion loss of the filter, and we measure the measurement is in red, and the calculate is in black. Good agreement also. Please next slide. And here it's in a chart. Sorry, dimensions were made using the double rigid antennas in an anechoic chamber with a pulse generator, then LTL, high pass filter, emitting antenna and receiving antenna. Transmitting antenna. And this is the anechoic chamber at the integrating and the testing laboratory at INPE. It's a huge anechoic chamber. Please, next slide. Here you can see the, I think, this is signal on the receive antenna, about 200 megahertz. And the signaling sequence showing the pulse repetition rate. Okay, this is in the receiving antenna. Okay, please next slide. Okay, we have done high voltage radiation, about 500 volts, because before, okay, I forgot to mention that it's about input puts about only 30 volts, 30 volts. And now we are injecting a square input pulse. Before it was a Gaussian input pulse with a peak of 30 volts. Now the peak or the flat of the rectangular input pulse is about 500 volts. Because you're using silicon carbide diodes with the blocking voltage on 1.2 kV. Then you can put much more voltage. This is important for high power microwave generation. Then we've got more at the receiving team, more voltage. Before it was in the range of millivolts. Now we're getting almost a peak of 10 volts. Again, we are measuring between the peaks. We measure 5 nanoseconds, which is about 200 megahertz of frequency generation. Also, we got a good match between SPICE, LT SPICE, simulation and experiment. Because you can, in reality, you can model the varying capacitance very easily using a command inside the simulator. This is very easy. And then you don't need to use a electromagnetic software like HFSS for simulating lamp lines. It's much easier to use a SPICE simulator. Okay, okay, that's okay. Okay, now more recently we have done high frequency generation with low voltage diodes. We repeat the. Please return to 2 or 3. More one. Okay, more one. More one. Okay, we use this in that table. We use it 30 sections using the same varactor diode. Okay, we got similar results. Please go ahead again. Okay, this one. And this one we've got, again, almost 200 or 300 megahertz, okay? And in orange or in brown, you can see here. Here in brown or orange is the first FFT one, the first line, because here we remove the C component. You see, we use 5 lines, and for 3, 4, and 5, we've got about 800 megahertz using low voltage director diodes. For line 2, 800 this line using varactor diode SVC 704, we've got 800 megahertz, but with SCV 236, we've got only about 2 or 3, the range of 300 megahertz. And that's the best high frequency generation that we've got using low voltage varactor diodes. Because if you want to use a high voltage, okay, if you want to use a silicon carbide diodes to generate 1 gigahertz, it will be impossible, because with high voltage, the PCB structure, the parasitic capacitance are much worse. You are not able to. I think we reach a limit here using PCB structure with LC devices. But this is interesting. For low frequency, we got one peak at 300 megahertz. With the others, because we use a BHP filter, a special filter to remove the C component. But we got, but the best result was 800 megahertz for lines 3, 4, and 5. Yes, no, 3. No, 3, okay. 3 also a peak at 400 megahertz. And 1, okay, 1, 300, and line 2, which is, okay, for 800 megahertz also. But the line 2 has a better FFT than line 4 and 5. Okay, please move on to the next slide. Okay, we try with the collaboration at Unifesp to fabricate BSZT sample, because it's barium, strontium, zirconium, and titanium. And where X is about 5%, they manufactured using the materials lab at Unifesp, and they developed these ceramic samples. We built an NTL using 10 samples with using linear inductance of about 3.3 microhenry, and we've got some nonlinearity, and in the experiment we achieved 5 megahertz only, because you use high inductance. Maybe you're using nano Henry induction, 20 or 30 nanohenry, we can reach more than 50 megahertz. But fabricating ceramic samples to simulate to work as nonlinear capacitor, it's hard. We are not getting enough nonlinearity to go up with the frequency. Okay, this is a problem. Okay, please next slide. Okay, now it's the gyromagnetic line experiment. We built in the lab. You can see the solenoid, the scope, the current source, and the voltage source, the pulse generator between 6 and 12 kV, with a rise time of about 2 or 3 nanoseconds. It also feeds the line with an input pulse with a Gaussian shape. You can use solenoid or magnets, and but we need an attenuator to see in the scope, because you have to protect the scope input. We built the line using a copper tube as an internal conductor, an AWG-18 wire, thin wire. We put through this thin wire the ferrite beads bought from Amidon Corporation, and the small beads, and we put inside the copper tube, and we are isolated with layers of Kapton. Okay, and then you can use permanents or the solenoid for them to construct the line, the coaxial gyromagnetic line. Okay, please, next slide. Okay, these are the best results that we got using a bias of 13 kiloamps per meter when we inject a 6 kV input pulse, but you have, because the system is batched, it's about, at the output, you got the half of the input pulse. Here, for the mode 3, we got with the 26 kA per meter and the 9 kV of input pulse. We've got a better modulation because we are using a high H field and a higher input pulse. What time? How much? I think it's until 9:45. Okay. 9? 8 minutes. Okay, let's move. Okay, Laura, next slide. Okay, here's the results discussion. The line is the ferrite beats are resonating precisely at 1.92 gigahertz, and the reason that we have to adjust the H field and the input pulse level. You have to do some adjustments, but the ferrite beats are also resonating precisely at this value, 1.92, and we have made some calculation using the saturation magnetization of the ferrite of about 3,000 Gauss, and use the magnetization factors. We calculate the magnetization factors, and we've got precisely exactly the same frequency. That we were trying to explain why, because our line is giving out the same frequency, because it's resonating at almost 2 gigahertz. Okay, but this, it's the same. Please, no, the last one. Okay, this is 2 gigahertz, about 2 gigahertz also. Okay, next slide. Okay, move on. Okay, now we done some experiments set up with magnets to replace the solenoid with magnets. And please, the next. we've got good modulation depth also, and 2 gigahertz again. But there's a problem with the profile of the magnets because, okay, here it's the key. Okay. Okay, thank you. We got also 2 gigahertz, a good modulation depth using, please, põe no último slide, não, o previous, o anterior, previous slide, yeah. Okay, because you use a short group of magnets, only 10 centimeters, but this was is enough to produce that modulation. I can use much to increase much the length of the neodymium rings. Okay, I could put more, but the low profile of the field will be bad for the oscillation, to produce the oscillations. Okay, next. Tá. Vai aqui. Ok. Tá. Ok. Ok. Ok, tá bom. Okay, this is the gyromagnetic line simulations that we have done using CST 3D electromagnetic software. Sorry, HFSS. Use also numerical simulation. We have done some comparison with the experiment. With CST simulation, we have done some trials, but it was not giving good modulation depth because we use 25 kV of input pulse. We've got only 200 megahertz. Then we pass to the HFS simulation. Okay, that we obtain a good fitting between our experimental result. Okay, using a 5.8 kV of a Gaussian pulse and setting the magnitude at 25 kiloamps per meter. We have also done numerical simulation with a 3D model proposed by Dolan. We use the telegraph equations for the transmission line using the TL mode. Okay, here we use the Landau-Lifshitz-Gilbert equation, the 3D formulation. You can see that it's very complex. Okay. We've done some comparisons with other papers. We got a good match here. Also, Caroline made some experiments, and now points are in green. We've got good result, better than, in fact, than Caroline result. This is his simulation, and our simulation is in green. Also with Priputinev, people from Russia. We got now only with simulation. They have done the Karat simulation. These are all numeric simulation. We've got a good match between their result and ours. Okay, these are the parameter values of the line. We can put the parameters of the line in our codes very easily. Okay. We have done the comparison with our experiment also, and the fit was not good yet, but we need to improve. Okay, this is one of the results of our experiment in black, and this is the numerical code simulation. Okay, these are the values, and the placed in the code with the line parameters. Okay, then. Okay, let's finish. Final considerations. Lump the nonlinear transmission lines, lump lines. I have a limit in frequency operation about 1 gigahertz. The problems are the PCB structure because of parasitic impedance that they limit the higher they limit for reaching higher frequencies. And the SPICE simulation have shown reliable, consistent with experimental results. And fabricating non-linear dielectric ceramic samples is difficult when need for operation range above hundreds of megahertz. And with geomagnetic lines, they are good for operating gigahertz frequency range, but a problem appears because for compact applications, then you have to use magnets. Here, for the magnets, you have the problem for low B field profile. Okay, you have problems with it's not flat. The uniformity of the B field profile provided by the magnets are not good. Then you have use a short arrangement, 10 centimeters. Okay, our bench compact lines test represent around 2 gigahertz, depending on the adjustments of the bias magnetic field and input voltage pulse applied. And comparing to other experiments, the frequency tunability is lost in our case because of the working regime used for operation of our compact geomagnetic lines, employing lower pulse voltage, less than 12 kilovolts, and the lower bias fields of HZ of less than 25 kiloamps per meter. We are developing a theoretical model to explain this phenomenon. We are working on this now. And for our experiment to increase the frequency up to 3 gigahertz of the same operation regime, the solution is to use nickel zinc ferrite beads from their cooperation with higher saturation magnetization of 4.7 kilogauss. Okay, we tried to use nickel zinc ferrite beads, but it's not working properly. We gave up. And finally, with simulations, electromagnetic simulations using software such as CFCT Studio or HFS have not demonstrated reasonable results in predicting the behavior of geomagnetic lines so far. The problem appears to be the polar tensor used in modeling the ferrite parameters in their built program coding, not decoupling well with the transient regime of geomagnetic lines. And the use of numeric simulations in the mathematical platform and solving the transmission lines equations, coupled to energy equation, appears to be a better approach. Yeah, I think it's a good approach, but but it's not reliable yet. We need to improve. In the finally, few authors have the console software with limited success in mud-distant lines. You can use a console, but there are problems too. Okay, and finally, sorry. For extending the time, the acknowledgements to my thanks to INPE, FAPESP, University of New Mexico, FUNCATE, AFSR, SWORD, and thank you for attending the talk. Any questions? Okay. With rectifier antennas.
Yes. They made a link with 1.6 kilowatts and 10 gigahertz.
Sorry.
1 kilometer long. I guess this is a very panel. It's a planar panel. It's a huge panel.
Huge panel.
And the link is about 1 kilometer long. And 1.6 kilowatts. They transmit and receive over there. And I guess it's a very impressive experience to be done on.
All right, thank you. All right, Okay, it doesn't matter, here it is. So I would like to talk a little bit about the research we do at Cosmiac. And Cosmiac started, correct me, Jim is the US sent big satellite upstairs, and the microprocessors that they use did not work very well, so we lost a multi-million-dollar satellite, millions of dollars up in space. It became junk. So, the Air Force decided to come up with a new way of building these satellites using reconfigurable microprocessors and systems, and that's how Cosmiac came in from the word configurable microsystems, etc. So the idea is to build those satellites to make sure that if anything goes wrong, to reconfigure it if possible up in space. So that's how the word Cosmiac is. And the interesting thing is that we started, is that gonna move it? Oh yeah, I'll move it, okay. So this is Cosmiac. It'll show that picture. We're about 30,000 square feet. And we did not start like that, but the person who helped us start Cosmiac, so I'm in Brazil, and that person who helped us start Cosmiac is in Brazil, Jim Like. So this is an amazing coincidence here. So basically, we have about 85, we have like 17 to 20 staff. The rest are graduate students and undergraduate students. We have a lot of facilities that I'm going to show you as we go on. We got contracts up to $50 million, but that doesn't mean we have $50 million every year. Those are contracts, and we get, money up to that ceiling. And I think, Jim, you gave us a lot of money over the years, but don't stop. So keep giving us the money. So our partners here, so you know, so we have the Air Force Research Lab. We got something called DARPA. We got companies, of course, like Axient, Veris Research, New Space Nexus. We got NASA. We work also with the European Space Agency. And our business is satellites, anything with satellites, communications, etc. And we're not into wars. We're just protecting assets like cybersecurity, etc., and communications. So some of the areas that we focus as a research center is telecommunications, and of course PNT. Positioning as GPS. The United States had its own GPS system, and all the world had the same GPS system. But now, and nobody was jamming it. Nobody's trying to mess up with it. But now, Russia has its own, Europe has its own, China has its own. Now everybody's jamming each other. So, because everybody has their own. So this is very interesting. So every country needs to protect, because if the GPS goes down, ships cannot navigate easily, and ships are the ones that move all the products, cars, foods, etc. Your banks, will go down, your ATM machine, everything. So GPS is very important. You will not even know how to drive in Sao Paulo. It's very complicated. So, so we do a lot of satellite development, rapid prototyping, 3D printers, metal printers, and to build things. During COVID, our center, which does satellites, because we have a lot of 3D printers, we will produce 5,000 face masks for our hospitals in New Mexico. So we can do these things very quickly. Of course, we do a lot of machine learning. Everybody does machine learning today. Space cybersecurity. We also started with Idol. Now he has an office doing directed energy. Directed energy, we're doing it. Mainly our interest is in satellites, because people are trying to destroy the electronics on satellites, and we need to have this to protect. So, and then we also got into hypersonics. I'll show you. One important thing, of our center is radiation testing. We have a lab which is just for radiation. What does that mean? Is if you take your cell phone, your computer, or any electronics up in space, it will not work because you've got swings of temperature, very cold, very hot. You also have all kind of radiation. So we do these tests. This is true for any satellite before you take it up, because you can have a very expensive, millions of dollars, and then it will not work. One thing may not work. That's how our center started. So we do all kind of tests to test these components. Companies come to us, they say, can you test this before we send it up? So that's very important. Otherwise, electronics are not gonna work up there. Satellite communications, here we have a ground station, and we can track low Earth orbit satellites 24/7, like every day, because those small satellites come in, they pass over our site in New Mexico, Cosmic, and you have like 10 to 15 minutes to get the data until they pass again. So this is very important for us to have this facility and capability here. And of course, we got all kind of antennas up there, all kind of frequencies. This is a big project, WV, that's 70 and 80 gigahertz, very high frequencies, because everybody's using the same frequencies, so there is no room to do other things. And of course, the future of satellite communications, like everything else, is moving higher and higher. And this is either why also directed energy is going up, because all satellites are starting to use, they've been using Ka, Ku band, and now they're going higher. Because when you go to very high frequencies, then you have a very high bandwidth, and you can download videos, and you can transmit things very, very fast, much faster than our frequencies now. And of course, a lot of these applications are commercial, because now they use 60 gigahertz. 6G is now trying to move to 140 gigahertz. So all these technologies are similar. So we're using them for satellites, but you can use them for terrestrial, applications. One thing I want to say, our center doesn't just do research and papers, which is very important for professors. We actually deliver a product. So here we have a product, a dosimeter that we built, we tested, and it's now in the International Space Station, and it's been there. I'm not sure if Jim, this is more on RF, not RF, radiation effect. I don't know if you funded that, so. All right, so we do a lot of remote sensing and machine learning. And what we like about machine learning is that there are a lot of algorithms out there, but we implement them. We design the chip in our place, and we implement the algorithm on the chip, and then we test the chip to see if it's going to work in space before we deliver it. Okay, so this is some of the products that we have delivered. Now remember, we're a university. University usually don't deliver very good products. They just deliver a prototype. But we work also with companies that can build a better prototype than us. So this is a anti-jamming and anti-spoofing device that we built. Brian Zufeld is one of our engineers, and we actually go there, White Sands Missile Range, where we test those things. We have play war games. Some people try to jam us, and we try to figure out the signal that is coming and the waveform, and we see if we can stop the jamming, because people can use that technology to destroy the GPS system, So. And we also want to destroy their GPS system. So this is a very important project, and I know correctly you're going to like that because we're using rectennas. But let me explain what happens. So this is a big solar, not one panel, huge, big solar panel up in space. So the top part is solar panels. Underneath is a phase array antenna. So this is underneath this solar, and you transmit an electromagnetic signal. So imagine having an earthquake or a hurricane that destroys the infrastructure. you know, you can, if you destroy the infrastructure, like in Turkey, they had that, the cell towers, you couldn't use any cell phones. So if you have batteries down or you have antennas down on Earth, you can receive that signal and charge batteries, etc. But we don't use that. We use right now this to charge, you know, beam energy to other satellites, and we'll show you something in here. But that's how it works. So let's see. Can you play the video? Okay. Let's see. Is it? Am I gonna be able? How do I play? Oh, here it is. Yeah. So this is a satellite with antennas on every face of the satellite. So if you can beam, this here is an antenna. We're just testing this, but this is a CubeSat. It's a satellite up in space, and it rotates in different ways, and every face has a rectifying antenna array, and of course you charge it from space. So this was for you, you know. So. All right, so our very famous guy, Jeff Bezos, believes, and I believe that's true, that all industry in 100 years, except drilling oil, you know, it's gonna be up in space, which means we're gonna solve our global warming, hopefully, and we're gonna have more space junk. But if you don't believe it, here it is. There is a roadmap, this United Launch Alliance in the United States. They have for the next 30 years, they know what they want to do. They're gonna, you know, this is, the cislunar region is above the geostationary satellite region and the moon. So we're gonna have like the solar panels will be your energy depot. It's like your gas station. You stop before you go to the moon and you charge your satellite or the vehicle. They're going to be pharmaceuticals being, you know, manufactured in space. They're going to be all kind of things that we do, everything in space. So when you travel from the Earth to the moon, you stop and you shop around. It's going to be a shopping mall up there. So, some of the other applications we're doing here is, I wanted to show, is 6G satellites. And everybody's talking about 5G, and we don't even know what we're doing, but 6G is the future. And in general for this, what we want to do with 6G, my work is mainly fabricate and test high-frequency antennas. So right now we're working on 140 gigahertz type of antennas. And there is some project here that I want to say that is what we call reconfigurable intelligent systems. This is a technology that now people are using or are trying to use for cellular communications on Earth, because you get a cell tower, transmits radiation to you, to your cell phone, but if you have those structures here, in every building, your window, you can actually manage to get the signal no matter where you are, and you can redirect it. So this is a big area of research now in antenna technology. Beamforming, this is very important. If you have a cluster of satellites, any country now, instead of building those very, very, very expensive big satellites, you can have a bunch of small satellites, call it a cluster, and you can do a lot of interesting things. So you can have a cluster of satellites. So you can use an antenna here, an antenna here, an antenna and here, and you can combine them and you can create a virtual array antenna. So I'll show you, for example. So I don't know why it's no, okay. So I got a PhD student at Sandia who is working to figure out, once you launch these satellites, they're not all online, they're not a linear array, they're all over the place and they're moving. Can you create an array and keep optimizing it constantly? So we're thinking machine learning, but you can use other techniques to beam the energy on the ground, you know. So those are some of the projects. So another thing that we do, we use a lot of software-defined radio in our lab. And we try, if you have, let's say, 3 signals, here is an array that we build. Can you figure out what is the direction of arrival? Because what happens is many times you get a lot of signals. Some are good signals, some are jammers, some are, you know, interference. Can you figure out which direction the signals are coming first? Then you do adaptive beamforming to make sure that you focus on the friendly signal and not your enemy signals. What else? So hypersonics is a very, very, very important area, because when those vehicles come from space into Earth, when they reach this Earth atmosphere, they start getting a lot of heat, and you cannot communicate. And you need to constantly be able to communicate with the ground. Of course, we have hypersonic now. Aviation, we want to be able to travel faster. So what happens is, when you have a plasma that is being created around your vehicle, the antennas cannot communicate. There is no communication anymore. So we build an experiment. This is a plasma machine. These are your electromagnets. It is a big, huge plasma machine, and we've got an antenna being behind this, transmitted. We have an antenna that we're receiving here, and now we're going to start our experiment. We just started this experiment, a hypersonics experiment, to see at what frequency, what angle you can go through and penetrate the plasma. And actually, we're going to do beamforming as well through the plasma to see if we can move. And of course, we're going to change the density of the plasma, temperature. I'm not a plasma guy, but we have some plasma folks to help us. So that's actually, every country is trying to figure that out, you know. So one area we work, as I said, a lot is machine learning. There's a lot of machine learning algorithms, but not all of them work very well. So what happens sometimes when you want to figure out where is the direction of your signal, the signal, even in regular communications, it bounces off a lot of places. So you know, the signal may be wants to come to me, but it may bounce there and come back to me. My cell phone may think the signal is coming from, but that's the wrong direction. So and it bounces from a lot of directions. And imagine when you have a lot of antennas, a lot of signals there, and a lot of reflections, it gets complicated. So our algorithm determine the exact location. It came from there. So, so then one area here, that's the last area I want to mention, is space cybersecurity. Everybody, in fact, yesterday, there was an article on CNN, everybody is trying to fight the war. The next war is all going to be in space. Nobody will be dying on Earth. Everybody will be in space. So, so this is a very serious problem. And it's like when people hack your computer, now they can hack your satellite. So it's very important, and they can do it with software, and they can do it with hardware. So this is one area that we work a lot. And you know, if you can mess up with the GPS system, but this critical infrastructure is your space, can be destroyed. And the Russians now say that we can destroy satellites. That's why we hired Ido, because he has high power microwaves. We want to destroy their satellites, you know. So, but we also trying to come up with solutions that are cheap, very cheap, because this would be the competition. Every satellite that goes up in space or is in space can be hacked, you know, so very serious. So, and in general, as I said, when you want to attack a satellite, you don't have to necessarily attack this satellite. You can attack the ground connection. So you can mess up the instructions that you're transmitting up to your satellite, and you mess it up. So there is a lot of links, a lot of weak links, or a lot of ways that you can attack your, you know, space infrastructure. So this is an area where you need computer science, computer engineers, electrical engineers, I mean, everybody, and that's the future here. And not only that, so there is also, that's why we do radiation testing. If you buy one component that you haven't tested for radiation, but also for cybersecurity forensics, they call it now. They test it to see if that part of the satellite is infected. Because you can put it, you have a very expensive satellite, and one part infects everything. And then you can infect other satellites in a cluster. Very complicated problem. So it's the future. I just want to show you some of our facilities, because Cynthia yesterday showed me her anechoic chamber. This is one of our anechoic chambers. This is a near-field measurement facility. We can go up to 100 gigahertz, but now we can go even more, so. This is a metal 3D printer, because this uses powder and a high-power laser, and we want to mix the powder to create different alloys to build antennas in space for space applications, so that they can perform better with these harsh conditions up there. This is your device here. It's a high-power microwave combiner. So, but one thing that we do very well is our university, so we train students. So training students is very important. And we love students. We have a small satellite, CubeSats. We build CubeSats, and we train students every year how to build those CubeSats. And we actually have launched a satellite years ago, and we tried to do that. So, this is at NASA, Kennedy Space Center, where we send the students to go there. So, again, students everywhere. Without students, we wouldn't have a university, so we're very nice to our students, We also work with companies. In the center, we have, you always have 5 to 6 companies that rent from us, they work with us, we write joint proposals, so we constantly interacting with industry. This is a place where we want to build the commercial part of space in New Mexico. So we're collaborating with other entities to create a space economy in New Mexico. I think that's it. This is our folks. We're very nice to our students. We feed them, we pay them money, we treat them very well, and we hope they're gonna do some work. So they do work, so. That's it. I don't have any other, so any questions that you may have. I like that picture. All right. Yes.
As you said before, in your lab, do you have DNA facilities up
Yes.
up to terahertz?
Yes.
And have you also probes and also the table to do on-wafer measurement? Do you have it?
Okay, the question is, do I have all the, yes, we just got the VNA, the vector network analyzer that we can do measurements up to 1.1 terahertz. For the radiation, we got probes up to 150 gigahertz, and we're trying to design our own probes for higher frequencies.
For on-wafer?
Those way, we got those. Radiation, yes, yes, yes. And in that case, yes.
Very small.
But we have companies that are going to work with us, Yes, we got a company in Albuquerque that build probes. It's called 3D Glass Solutions. They build it in glass. And so, yes. And but when you do radiation pattern measurements, for the VNA and the wafer, we've got that up to 1.1 terahertz, because we work with the photonics folks, and we work a lot with the photonics folks. Yeah. Yes, go ahead. Cynthia first.
The radiation problem, how is the biggest in measurement?
In the radiation, theoretically 1.1 terahertz. Experimental.
1.1?
Terahertz, yeah. But we haven't done it yet, but we can, because I need to do, see, for these high frequencies, you don't need an anechoic chamber. Exactly. On a table, yeah. Yeah, we got the positioners, yeah.
And the components, I listen about the airboat.
Erva.
And so what is it?
Oh, you're talking about a company that does what? Probes?
The company, not
Okay.
the company with the name is Airbus. They
Oh, yeah. Actually,
must say Sagi in the text.
yes, we bought some antennas from them that hypersonics experiment. We bought antennas from them. Yeah. You should volunteer to come and work over. Correctly.
Could you please show me the rectangle? Do you know what's the topology of your rectangle?
Yes.
Looks like.
Actually, I did not build the rectangle because the project started before I joined the center. It was the Navy research lab. It's 4 antenna elements, and they're all connected to the center of the diodes. So they all feed, I think there may be a couple of diodes to feed. So it's modularized, 4 elements, 4 elements, 4 elements. Each 4 elements have a diode and a rectifier. So that's why, but every phase of the satellite, because the satellite is moving around, we're not in space, and the antenna beams, you wanna constantly, charge it.
I published a paper with one criterion to decide about the best topology of rectangles. Bow tie, spiral, square, and just one criterion.
Yeah.
To identify the best one.
Yeah.
But it depends on the distance between them.
The distance, the polarization, all that kind of. So send me the paper because I can tell you, no one knows perfectly because it depends on the application. The topologies should be different for different applications. So if you send me that, we can look at it, yeah.
I know you know everything.
I don't, yeah.
There is a new kind of antenna, not a very new, plasma antenna for 6 years. Plasma in lato sensu, because the plasma is a collection of electrons under the semiconductor plasma also. And this is very nice antenna for application 6 years.
Yeah, okay, that's a good idea. I do know about plasmas in tubes, and you can do things, but I did not think of it about 6G, so that's a good suggestion. Thank you. Yes, sir.
Is the relation of the COSMIAC project and the program engineering for peace?
Oh, wow, that's a very difficult question. I can tell you this. So the question is, what is the relation of COSMIAC, because we're a research center in a university, and peace engineering? The one thing we're doing that I like a lot is space power beaming. When you beam power, because space, you collect solar from space down to the ground, you can deliver energy in any part of the world. So there's a poor area, let's say there is flood, there is earthquake, there is hurricanes, you can help that area. You can help the poor, and any country can build this now, and they can have energy that comes in without relying on oil or anything. That's an alternative energy, which I think it can help poor communities, etc., all over the world. So that's one thing. Now, the rest is communications. I mean, if you don't have good communication infrastructure, your cell phone is not going to work. And then there are going to be more wars because people will be fighting with each other. When you have good communications that everybody can, and you can protect people, so I think, you never know. People can switch things and do whatever they want, but I think it's part of it. Yeah. All right. Coffee time? Coffee time. Okay. That's it. Thank you. And this worked very well.
Let's go ahead with our workshop. And now we have Professor Gilberto De Martino Januzzi from State University of Campinas. Professor Gilberto works, research about energy systems, planning energy systems. Thank you.
Well, good morning, everyone. I think my talk is going to be a complete departure from the previous ones that I heard, but I hope these can address some of your interests. Well, basically, part of my work over these last many years have been dealing with intersections between policymaking, technology, and energy poverty as one of the issues that I have investigated. So in this brief talk, I'm going to sort of, I will move from cooking, basic energy needs, going to distributed solar energy, and ending into what I think is becoming more and more relevant is cooling in places like Brazil or New Mexico as well. Okay, so I will go briefly on cooking, but I will dwell more on distributed generation because I see as the technology has a great potential to address some of the huge inequalities that we have in this country. And if we don't do anything, these inequalities due to solar energy can increase, which is a paradox. But the way electricity tariffs are designed, the more distributed systems that we have, which are owned by high-income customers or residential customers, the greater the electricity tariff will be, because the utilities, the way the regulation is set up, this will distort the electricity prices, and the poor will pay even more higher tariffs if we don't do anything. And so let's start with cooking fuel, which was where I first started to work on this area many years ago. And Brazil is a very interesting and successful case where we had a transition. We had an energy transition in the 60s and ended around the 90s from solid fuels, basically fuel wood and charcoal, to cleaner fuel, which is LPG. Brazil is a huge country, and we cover 99% of the residential market with LPG at the moment. So, and it was done, as within a strategy to transform the market, the cooking fuel market. First, introducing universal subsidy. So the LPG was very cheap to all customers, and as time passes, we moved towards a more targeted subsidy towards the low-income population. All this transition was not easy. There was some bumps along the road. And now I see as a new challenge, we have to now have another transition, another energy transition away from LPG, which is a fossil-based fuel, towards alternatives that the technology is not a technological problem, is much more of public policy, market transformations, or another way to introduce this. So I'm just listing some of the paper we did. This was 2004. This was just when we were moving away from universal subsidy, because it was all customers, rich and poor. There was a unique price for LPG all over the country, and in the early 2000, they were moving away from this strategy of universal subsidy and looking for the poorest consumers so that they could afford the LPG. But this was not an easy transition. And this was one paper that we produced studying what was going wrong, because what happened, it was a huge price rise, and what we had was a reverse situation. Most of the poor consumers were going back to fuel wood and charcoal, and so we had to solve that problem. In this is Energy for Sustainable Development. I am one of the editors of this journal. In 2004, we had a whole issue discussing clean cooking fuels. So it's not a new debate. And this issue, we cover a lot of several technologies, several experiments in Africa and Asia, addressing clean cooking fuel. For those who don't know, the use of solid fuels in Africa and Asia is still a health hazard, a significant health hazard. People die, especially children, women, and old folks. They still have problems with the smoke, the indoor smoke, the poor ventilation, the poor cooking devices. And all this is not a huge technology problem. This is we know how to deal with that for many years. So it's a matter of other things that need to be in place. So as I said, Brazil is a very interesting case of a country that could move away from solid fuels. And there was, I list here some of the ways we dealt with the problem. At that time, Petrobras was is still the main public company, and it was very instrumental in producing the LPG and controlling prices. So the government had a very important power in order to control LPG prices all over the country, and so it could, deal with subsidies as a sort of a central piece of their public policy. And the interesting thing was all the distribution of LPG was done privately. So it was, although it was a very monolithical military government, all the LPG distribution was done privately. And it was an interesting case to regulate how these guys could, have profit and at the same time deal with a commodity with a fixed price. But anyway, so in about 20 years, the whole country could have a very reliable network of LPG distribution, and the dissemination of a cleaner fuel was in place. But the exit strategy, this was done in the late 90s. Then we had problems, which is now being corrected. Now it's a much better system, which is we have is within the social basket. LPG levy is many state governments also have special prices for the low-income households. But anyway, the challenge is now what I call the second energy transition. We know all these technologies. We know ethanol is an interesting cooking fuel as well. There are devices to use that, but instead we use ethanol for transportation. But cooking market is also something interesting to look at. It's not a technological problem, as I insist, but we need alternatives to move away now from LPG, because we are also captured by LPG. The whole country depends on LPG and a little bit on natural gas, but we need to move away from these fossil-based fuels towards renewables. So cooking energy transition is something which I think represents a challenge, especially if we look into, to the lower income population. Well, now I think I would like to spend a bit more time. This was work done over a 2-year period. We just published this year. And the idea here is to, as I said, distributed solar in Brazil is expanding very rapidly. And what is happening is that utilities have to be compensated by their loss of revenues, their losses of revenues, right? And the consequence of this fact, we all want, solar energy to be disseminated, and so, but there are some problems with that, and it hurts more the poor population, because what happens is the average price, tariff, electricity price has to rise due to the regulation. And it will hurt the poor population that cannot afford the solar system, right? And has to rely on the network, the electricity distributed by the network. And I had this idea to use, we have a subsidy for low-income electricity tariffs. It's significant. It's about 60% of the average price. So it's but this is subsidized by all the other electricity consumers, right? And let me show well how we mapped our audience. I mean the potential clients for these mechanisms that we want to put in place. We wanted to replace the subsidy, the social subsidy, for distributed solar. We wanted to have the solar panel in the poor households as a way, as a exit strategy regarding the electricity subsidy. This is, and we combine 4 indicators. One is the social indicator. So we mapped in the country those households with low income, those households where the chief was a woman, because many of these poor households, they are sort of, a family led by women. We mapped the solar irradiation, and we also mapped the tariff, the local tariff, and there was another one, I can't remember now, but this is the kind of map that we got as a result of these indicators. The reddish parts are where there more potential, more impact of using solar to address these social issues, income issues as well. The CAD Único is where we got all the poor households. They now are registered under this CAD, this data set. This I just want to show. Electricity tariffs in Brazil is a very nice way for the government to collect money from everyone, and no one knows about it, you know. And but there's a lot of things here, even subsidies to coal goes into the tariff, the average tariff that we have. But let me see if I can, yeah. And what I want to show here is this orange part, which is the subsidy that goes to subsidize low-income households. It's not, you can see this not a huge one, you know, you spend more money going to subsidize coal generation than goes to the social tariff, but it's about $500 million per year for the whole country. So it's a lot of money. And the challenge that we have here, the exercise that we wanted to explore was to use this money in order to subsidize the purchase of a distributed solar system and put that in place, and at the same time see if that consumer could pay the regular tariff instead of the, so we were substituting this annual subsidy to capex on the technology. And all this paper we had two kind. I mean, if you are interested, I encourage you to take a look at the paper because there are too many details which I cannot explore at the moment. But and we presented this to the government, to the development banks. I mean, they found this reasonable, no? But we wanted to see where in the countries this would hurt the targeted audience that we didn't want to hurt, and how it would also benefit the whole system. Because as I said, these subsidies go, I mean, it's coming from us, you know, from your regular tariffs. We are subsidizing the low-income households. So there must be, and that's another problem that we have in Brazil and many developing countries. We are very smart at creating subsidies, but we don't know how to take them out of the scene, you know? And we change the names, but it's there, you know? Once it's there, it's sort of forever, no? So that's, we produced several maps, and this was I had a very good team working. We worked at the municipal level, so we could get, and data is, Brazil has very good data for those who are coming from other places. And so we mapped the whole country, and there's a gradation of colors, but I will explain later. And we did more detailed simulation in those areas. In São Paulo, in Paulínia, we used Paulínia as one of a reference case. In Rio, in Minas, all these places, they have some differences according to social strata, solar irradiation, tariffs, you know, and so we simulated a lot of cases. And we had two kind of configurations. One was each house would have its own system. It's a distributed system, and the other was a sort of a mini grid, or a system where you could have a larger plant serving several households. And the economics is different. The impacts are different in both cases. But if you are interested, please take a look at the paper, because there's so many facets on the configuration, on the tariffs, and the solar radiation. No, but as I tried to point out here, this is and we also simulated the ECMS is a sale tax that goes into the, and that also makes a difference. So the government is also part of the solution. It has to think whether it makes sense for them to not collect sale tax on electricity for the poor, because they pay also sale tax as well. So this is one configuration, just to show you the colors. We were able to see the impacts on the poor consumers and also the other consumers, because as I said, we also pay the subsidy that goes to the poor households comes from the average tariff as well. So if we can eliminate subsidies, we potentially can benefit both consumers, the average consumer and the poor consumers as well. And the green is where this could happen in the whole country. So if we take out the subsidies, considering this system, and in this simulation, we also took out the sale tax. It makes a difference. It's about 20% of our electricity bills is governmental taxes. So it makes a difference. So it's a combination of things, that will make a difference. And so this is the sort of key to these figures. This is the situation in if we have each household with a solar generating device. So the yellow part is where there isn't much difference, and the green part that there will be. I wanted to also briefly show the. Can you? Você pode pôr o artigo? Yeah. On the paper, we do have more information. I just want to illustrate more what I'm talking about. But it's not a crazy idea, to think of solar distributed generation as an exit strategy to move away from the social tariff. It can make a good solution not for the whole country. That's the tricky part. It's very it has to be very targeted. So if we just move down, maybe I can do this. Como é que eu? Mas não consegui mexer. É só apertar?
Uma vez e vai baixar aqui.
Não.
Uma vez, ó. É igual só.
Ok. Então deixa assim. Yeah. So, we spent a lot of time devising these maps. This is the solar irradiation, for example, right? Which is, very concentrated in the northeast and central part of the country. These are so, there are many simulations that makes our argument stronger, and it's not a crazy idea at all. It does make sense, but we need very important modifications in the regulation, and because we have a regulation that applies to the whole country, and this cannot be, you will create more problems than we can solve. So it has to be very localized changes in electricity regulation, subsidies, for this to work. But it's one example of how cutting edge technology can be a way to address energy poverty, and everyone wins. If we don't do anything, the situation will get worse. And we will always try to fix a little bit and then create a greater problem. So I just wanted to illustrate. If you are interested, take a look at the paper. It took us a long time to develop, and we discussed this with development banks, with everyone. See, it's a sexy way of looking at things, but needs to be implemented. My last contribution is now. Podem voltar pro PowerPoint. It's something which I haven't developed fully, but I do have very good indications, and it's regarding space cooling. I had one student that produced a very interesting combination of information regarding hospital occurrences with the low-income population, especially regarding kidney failure, heart problems, pressure, in Campinas. And we related that to the increase in temperature. So can we move down to maybe the last slides? Yeah, that one. This is one example of satellite. So we also work with satellite imagery, looking at the surface. This is the municipality of Campinas over time. And you can see there are a trend. I mean, we know that, right? But we can picture that trend of increased temperature in the municipality of Campinas. And it's greater in the areas where the poor population live, because there's lack of, the dwellings are poorly insulated, lack of vegetation, all conspires against, And I had colleagues at the medical school here at the university hospital, and it correlates very well. This is something I need to develop more scientifically, but I do have very strong hypothesis in the making, right? Because there's a very strong correlation between the hospitalization of this population and extreme or heat waves that have occurred, So this points me to the need of addressing cooling strategies, which can be passive cooling. I mean, there's so many. I mean, this, again, is not a problem of high technology involved, but it's putting technology to work where it's needed, right? And this will save a lot of, working hours of this population that has to be hospitalized, sudden deaths, There's a social cost involved, which can be avoided. So this is one area which I want to explore a little bit, but I just wanted to have you a glimpse of the way we are looking at these problems. I can't remember. These are temperature chart. I can't remember now, but I will find out. Okay, but these are satellite. Could be, yeah. And those are the satellites, and these are the trend. This was done by this student who is not here any longer. He was from Germany. He's from Germany anyway. But this is another area where I think we need to develop strategies, how to address cooling strategies, looking at the building code, looking at the vegetation, and even artificial cooling in public spaces, which is something that is being done in other countries as well. Well, I hope I sort of gave you some ideas on how to address energy transition and more social equity as well. Thank you.
We are open to questions now.
So, how do you do to help the poor in the US? Anyone get a tax credit if they put solar panels? 2-3 years, but then the government changes, they cancel the program, they start again, depending on the policy. Yeah, but you're gonna have to install the solar panels for the poor, because that's expensive. So who pays for that? The program? Who pays for the solar panels?
No, you see, the way it is, it's a market-based mechanism. So if you have money, you put a solar system. You have a good house? No, the poor, they don't have that kind of assistance. No. No, you have this break anyway, okay? What we try to do is that we don't want to keep this break forever. We want you to be a regular customer, right? In order to do that, we are going to see how we can provide a solar system so that you can meet your requirements and perhaps sell electricity to the grid. And then you also generate income, okay? So, but this it's a hypothetical case. The poor don't have these incentives or break or financing mechanism. Even we also simulated an increase in cost because you need to reinforce the house in order to the roof in order to accommodate the equipment. So.
I have another question. I mean, here in the United States, they try now, not everywhere. When they build a new house, they build it. It's what we call green, where the windows, the walls,
Sure.
everything.
Sure.
And if every house becomes like that, it will be less energy.
Right. Right.
Less water, less this. You guys have that problem.
Yeah, we have something like that, but as far as now, we have that for commercial buildings. Okay, so and we have special certification, and they like to this is kind of their marketing as well. So but we are always talking about the richest strata, the ones that can afford or know they know they have the information already and they can solve by themselves, right? What was our concern is that if we don't do anything, even a good solution like solar energy will hit the poor the hardest because the tariffs will rise, because that's how it works, right? And we wanted to get out of the subsidy. That's my approach. We don't want to have subsidies forever. We don't want poor. No one wants to be poor forever, right? You want to be a regular customer, so you need to pave that way towards this idea. Sure.
I'm really interested in what you presented here. This is the program that we created at Unicamp Engineering at an undergraduate level. So we developed a dashboard for the state, measuring water, air quality, health, issues with health, asthma, cancer, a lot of cancer because there's a lot of contamination, combining labs and all of that. And we're getting into finance. So we started the dashboard, we're about to release, and this is for undergraduate students, and using high tech. Sensors, satellite imaging. The other thing is finding trusted data.
Yes.
It's not the data, like, I'm glad you said you have good data. It's not easy to find.
It's not easy, yeah.
Okay? So the next stage is we're gonna get into policy. Either, is there a policy? No. If there's no policy, how do you design policy?
Yes.
Okay? The other thing is, access to the law of justice. The rich are okay, but New Mexico is one of the poorest states. Okay? The highest incidence of COVID deaths were in New Mexico, where we have the best national labs, okay? Because the Navajo did not have access to water or energy, much less telecommunications.
Right.
So we have to address that, and this is what I'm doing now at A&M, with all undergrad students. So I would like to really establish a dialogue, because I think we can learn a lot. And right now, the other course that we're doing is teaching undergrads demystify machine learning, AI, and processing. So it becomes a tool. Everybody talks about AI, nobody knows what AI is. I do.
Lucky you. Yeah, he's going to give a talk. Yeah.
So I just want to say that, but I really want to establish a contact.
Sure.
Because,
Uh-huh.
I'm here in presentation, but 33 years ago, with Unicamp, we started a very active consortium, holistic. Okay, that has done a lot of things, not only in Latin America, but worldwide. So under that is that 30 years ago, we decided to use the language of science and technology for peace and unity.
Okay.
Because we thought politicians are not going to change laws of physics. They can change the laws of physics. Okay. But I just want to say that I really like your talk.
Thank you. Sure. Yeah, this is a policy paper. So we wanted to.
Right, and there's a lot of collaborators that are working with access to justice as well. One is from Stanford, the other one. I'd like to introduce you. There's a symposium that will be organized by USP in November. We'll be coming back, so let's.
Okay, sure. Thank you.
Thank you.
Thank you.
You get more time. You get more. So Krista's going to talk about AI.
I have one more question. When you say from 2015 to 2018, there was more people getting sick and all that stuff, you said it's the temperature. Because
Yeah.
that's
No. I'm forcing the bar here. Yeah. Yeah. No, it could be a lot of things. Yeah. No, as I said, it's an indicators. I haven't developed this. Okay. But there's a, I would like to see how could be. It's a sort of a weak correlation, right? At the moment, but the international literature is proving that as well. So maybe it's we need to look more with more rigor, like a scientist. But I think there's a good indication that something is happening, right? Something is happening. Landsat. Yeah, that's right. It's the satellite we use. Yeah, right. No, but because we also did a lot of work on the new standards for air conditioning here in the country, in Brazil. And again, but we haven't done anything for ventilators, for example, which is a much cheaper cooling device, right? And we don't do anything with low-income building. I mean, if you look at the social housing, it's like a greenhouse, huh? like a box. It's a greenhouse. So even the social, this is a very basic stuff. You know, you should start with cooling or addressing climate change or energy transition. Like that's my topic, energy transition, right? In dealing with building codes, materials, you know.
Because
Transportation, yeah. Yes, there's heat islands. I mean, if we go, if you have a greater detail satellite, you see the hotspots in the country, and even in the poorest areas, they are becoming hotspots because of the building, the materials they use, the lack of vegetation because they cut down things. They need to be re-educated, right? So there's simple interventions that we are losing track, and this is causing harm. If they're ending up at the hospital, that's another thing. But it's well, it took us 30 years to disseminate. I mean, yeah. If you can help with AI, I think I would get rid of many people here. No, it's a sort of, I mean, the way I approach this is an intergenerational way to look at the things. But if we don't start, it's going to be a problem. Yes.
We have here in the new building, if you walk to the São Paulo or the cities or the center of computing new buildings, they are glass and glass and more glass as we have in Oslo, okay? But in Oslo, you need glass because we need light. And here we have a lot of sun and glass and glass and glass.
It's a greenhouse.
And you have to air conditioning. If I put one big wall of 3 meters in my house, completely in glass, I will need to cover a little bit, and also I need to
there is thin film that goes now on the
Yes, yes.
that they change the color and the reflection.
Yeah, there's double glazing.
But you
No.
need to use this.
Yeah.
I think it has-
But all these are also very costly,
Oh, yeah.
right? So,
Everything costs.
yes, but there are some low-tech interventions, building design, city design, that has to be addressed at the moment. Yes. Yeah, that's urban design.
You cannot block everything.
Cynthia, you should go to Alaska, it's really cold.
Then I can use
Yeah.
Here is not so.
Yeah. No, Brazilian is interesting. Yeah, it's a lot of things. But, I was, in Brazil, we have a committee that regulate, I mean, we certificate equipment, energy using devices, equipment and buildings as well, right? And for some things it works. I mean, like the air conditioning thing that I was talking about, we don't have the best label yet, but we are very close. So we have some policy instruments. What we have is, I mean, and I'm sure you're going to understand this. We have very bad decision makers and politicians, but the instruments are there. And we have good experts as well. Building codes. We have building codes, but as I said, they don't apply because it becomes impossible, right? To regulate, to inspect, to make inspections. So there are many other problems. But many people know how to do things, and we didn't need the EI thing. Yeah.
Thank you very much, Professor Januzzi. Thank you very much. And now we have the last talk of today. Professor James Like from the User Force.
I sent some slides and they made it. If not, I can do without.
You want to use my slides?
Oh, okay. I sent to Ugo this morning. So while he's pulling the slides up, I'll just explain a little bit. So I work for the Air Force Office of Scientific Research, but I live in South America. I live in Sao Paulo. And my mission is to find and fund the best science in Latin America. Okay, great. And I'm going to talk about that here. Okay. Thanks. The Air Force Office of Scientific Research is also part of the Air Force Research Laboratory. The United States Air Force has a service laboratory. So the Air Force, the Army, the Navy, we all have laboratories, and the Air Force Research Lab is the one that handles the Air Force. A part of that is the Air Force Office of Scientific Research. The difference between AFRL and AFOSR is, I'm sorry, this is a different version, so I want to make sure I'm not confusing you too much before. So let me start with some definitions. So SWORD is the Southern Office of Aerospace Research and Development. We're based in Santiago, Chile, and Sao Paulo, Brazil. We are part of the Air Force Office of Scientific Research. AFOSR is headquartered in Washington, D.C., but we have offices in London. That was the first one right after the Second World War. We realized that the best ideas are not just in the U.S. We had the Manhattan Project. We want to find the best scientists anywhere in the world. And by funding basic research, we're advancing we care about the Department of Defense. We're supporting that, but the best ideas help military as well as commercial. If I can make a stronger steel or a stronger metal, that is useful for airplanes, but it's also useful for bridges and many applications. So we've set up an office of these, or a network of these offices. Similarly, the Navy, U.S. Navy and the U.S. Army, they have the same needs. And we also have offices for the Navy and the Army. So in Latin America, there's probably a half dozen people like myself who go around the continent looking for good ideas. So we actually do fund work at Unicamp and University of Sao Paulo. We fund a lot in Brazil, but we also fund in Peru, Colombia, Ecuador, Dominican Republic, and other parts of the region. So one of the difficulties I run into is explaining to people what basic research is. I think academics understand this, but we still find that, companies like Petrobras are supporting a lot of research, and they tend to be focused on near-term results, things that are going to benefit in the next year. We're looking for ideas that may not be, they may not see reality for years, but they may be profound. I mean, we're actually looking for things that are worthy of Nobel Prizes. And so we have funded a lot of research with people who eventually got the Nobel Prize. So I think what we like to say is that we don't know where the next Nobel laureates are, but they could be here in Brazil. But we have a high bar in that we want to fund basic science. And this idea of basic research is something that we very much are committed to. So I don't know if, I have found at different campuses that some people don't know what technology readiness level is. Does everyone know what TRL is? Heard of it? Okay, good. I won't have to explain this too much, but we fund, the TRL 1 ideas. Most of the Air Force Research Lab and groups like DARPA, they're funding the advanced 6263 research. Now, there isn't as much money in basic research as there is in applied research. So it's very important that we stay focused on basic research for many reasons. And one of them is that because there is less money in the pool of basic research. That's the first thing. The second thing is actually more practical for us. We don't do classified research. We do open academic research. So when you start working with DARPA and the Air Force Research Lab, you often get into restrictions, export control, classification. We have none of those issues. That's why I'm able to go all over the place and talk about what we do and to provide funding. There are no strings attached. We want you to publish, and we get benefit from that. There is, if you work with the Department of Defense, there is this bureaucracy that was that goes back to, I think, Eisenhower's, the military-industrial complex. So we've codified how research is categorized. So we use codes like 6.1. That 6.1 is basic research. 6.2, that's what DARPA does, and AFRL. 6.3, as you get down further, you're getting to the GPS satellites and the aircraft that we procure. But the Air Force Office of Scientific Research controls all 6.1 funding. So that's, and we take that quite seriously. So in Washington at the Air Force Office of Scientific Research, there are these portfolios. So there's about 36 to 40 of these boxes. Each box is an individual in Washington that control 30 to 50 individual projects. We are remote outpost for this office. So there is an individual that is, for example, doing biophysics or complex networks. They're in Washington. If I get a proposal in complex networks, I have some expertise in that area, but I will probably go back to them to share that proposal. And I'll talk in a moment about how you can work with us to get grants funded. But we have our own expertise. My background is in microelectronics and space. I lived in Albuquerque for 30 years, and I worked with the Space Vehicles Directorate. So I was part of the Air Force Research Lab before I came to Brazil. We can't afford to put 40 people in South America. So that's why a small number of us have to actually run interference and coordinate with this larger group. And this group itself is, again, the 6.1, the basic research part. So there's a 2,000 person network of the Air Force Research Lab in different parts of the country. And so we also reach out to them for coordinating the ideas that you propose with us. So this is our office. We're a small office. Colonel Greenwood and myself are in Sao Paulo. Colonel Harmon, we actually have a new major. They're in Santiago, Chile. Now, I've tried to explain a little bit about who we are. I want to explain how you can work with us and help us find the best ideas. We do three things primarily. We do a lot of other things, but these are the three things that we do most often. The first thing we do is we fund grants, research projects. They typically are 3-year efforts. They can be 3 or 4 years. They're about $50,000 US per year. So they're not large programs, but we have the ability to award to any academic institute. There's some paperwork requirements, but we like to start with white papers. White papers are like abstracts of your ideas. So if you can write a white paper of your idea before you submit a grant proposal, because that's a lot of work, we can work with you. And sometimes I've gone 3 or 4 cycles with researchers in Brazil and other places to get the white paper to a point where we have a very strong, defensible, basic research idea. When you do that, we have the ability to then have you submit the grant and most likely get the grant funded. The second vehicle we have is conference support. We can't pay for 100% of a conference. We can pay for about half of the cost of a conference. And I don't make those rules up, but often that will help because if you have other sources of funding, we can help. So I'd say if you have a Nobel Prize winning idea, give us your white paper. If you don't have a Nobel Prize winning idea, do a workshop. Workshops are about topics. They're a great way to bring people to South America, to energize collaboration so that we can also get white papers from the result of that. The third thing that we do, and this is a very underrated program, is we have something called Windows on Science. So we can send you to the US. I can send you to the Air Force Research Labs in Albuquerque, Florida, New York, different locations. Those programs are very valuable. I used the Windows on Science when I was at the Air Force Research Lab to work with Sweden. That was from our European office. And we turned that into a $6 million collaborative program. So that all started with one researcher coming to Albuquerque, giving a seminar, one that I saw, one that I got very excited about. I asked for a white paper. We funded the grant. We then did an international program. Now, Brazil is one of the few countries in South America to have what's called an RDT&E agreement. That's a research, development, test, and evaluation agreement with the United States military. So that means you can do these higher value collaborations. So we at AFOSR, we can provide seed grants to help provide momentum to larger joint research programs. And I can help you learn more about that. That's not my primary mission, but the RDT&E agreement is a very powerful, and it took a long time to get that agreement established. So I would like to see it get used, but we can provide supportive grant, support for grants in anticipation of those other programs. So the Windows on Science is very good, and these are the 3 tools that we have. Also, I mean, because we are based in South America, it's easy for us to go down the street to University of Sao Paulo or Campinas like I did this morning. It's easier for us than to come from the United States down here. So we can provide a lot of coordination for other of our colleagues. And that's kind of it in a nutshell. I appreciate a chance to participate in your workshop and tell you about our program. We have funded over 300 research grants since the office started in 2009. And we've funded over 100 projects with Brazil. And a handful in Campinas, quite a few at University of Sao Paulo. I know in a couple of weeks I'm going to be bringing some colleagues to Campinas. I think we're going to see the facilities that we're going to see today, Sirius and the nano facility. But anyway, very excited to be here, and I would be happy to discuss things with you further. I have some business cards with me and would love to hear from you. And I'm already working with some of you. So thanks for your attention.
I have one question. How are the proposals we submit, how are they evaluated?
So the white papers that we would get from you, we will, if we have expertise or the proposal has obvious concerns, we'll work with you. We'll find the right experts either in Washington at AFOSR or in the laboratory, could be in Albuquerque or another location. So we'll try to get feedback from those assessments. They're very informal. This is not like working with the National Institutes of Health, which is a very grueling evaluation process. Ours is actually very simple. The other thing that I do, and I briefly mentioned that the Navy and the Army also have equivalent offices. I work down the hall from a Navy and Army person, so I'll share often the white papers. I'll say, hey, this looks like it's more useful for the Navy, or maybe we can join forces. I often co-fund projects with the Navy. It makes our money go further. And so to us, every grant we fund is a win. It's a win for us. It's a win for the researcher. It's a win for their institute. We'll try. Now, often I will get ideas that we just cannot, no matter what we do. I'm working with one from Columbia. It's about spacecraft propulsion. And there's just no way I can make that basic research. So I said, look, we cannot fund it, but I have colleagues in Albuquerque who do the applied research. So I share that with them. The white papers, it's an important commodity because I can send it around. And so they actually are interested. Now, I won't probably be doing much with that, but I've helped connect some people. So we'll try to do the same thing. We work with the State Department. My offices are in the consulate, Sao Paulo. So we also come into contact with Education USA and USAID, and the State Department itself has projects. So we'll try to help find another home for an idea. I mean, we like to try to help people, not just slam the door, just say, well, this is not a Nobel Prize. I don't care. Where's the next idea? We'll try to work with you.
How do you manage or deal with IP?
We deal with it by letting you keep it and getting out of the way. We have no interest, because the best thing you could do is to take that idea and make a lot of money for Brazil or yourself, or just improve. I think it's actually hard to work with IP. I see a lot of IP when I was at AFRL. We sat on a lot of IP that it can get entangled, but we don't want to get entangled with IP. So we will ask you to publish a lot. So sometimes we do have a problem where people want to do secret, not military secret, but secret to them, proprietary research. And we say, well, we want you to publish in open, journals. So, but we will not put restrictions on your intellectual property.
Is possible for together with small companies?
We fund, this is just like the way AFOSR works in the US. AFOSR works with universities and academic institutes in the United States. We work with academic institutes, nonprofits in South America and Central America. For whatever reasons, that formula does not include small businesses. Now in the US, we have a small business innovative research program. That's an engine that funds billions of dollars of research. We do not have the equivalent here. And I wished we did. But what we find is a lot of the small companies are working with universities. So we can often work with the university. And it's good if they actually partner with the small business, because that offers more prospects for transition. We like to see transition. It's not a requirement. We expect you to give us crazy ideas, and those crazy ideas can fail. They often do. But what we find is that sometimes people have ideas that they never get to work with because they're now caught up getting funding from oil, gas, those interests they have, they don't want to fund your idea, but we might want to. We are, for example, working with a group in Rio de Janeiro called IMPA, and they're like a mathematical institute. And one of the individuals has a concept for finding the most way to stack spheres. Now, when you go into the Feira Livre, the open market, you see the oranges stacked. That's a hard math problem. It's been solved. The difference is this is a 5-dimensional orange, and we've never seen, we don't know what that looks like. But and we don't know why would that solving that problem matter. But this is the nature of basic research, is that sometimes we look at problems that don't have an obvious application. It might be with curvature of space-time and some other things. It has some connection to some future quantum problem. But for now, it's just a really cool problem. And INPA is the only field medalist, I think, in South America is at INPA in Rio. So we've been there. It's a very interesting group. But we do like to look at crazy problems.
Support for a conference, support for event itself, or for individual research?
Yeah, well, it's usually support for the conference. Like, for example, there's a wireless conference, IEEE, in Rio in July. I think we're going to work with the Navy on providing support to that. We get about, I want to say, a dozen a year conferences that we're supporting. It's for the event. I mean, if the researcher, you know, it might be travel for some individuals. So it might be a cost that by providing that support does help the researcher. But it's not like for paying salary, not for a conference. That would be a normal grant.
So is that a set amount, or it's a percentage of expenses to run?
It's a more percentage, but I mean, yeah, but it's like 30-50%. We can't, I wish that we could fund 100% because sometimes, it can be. I mean, if you're with IEEE and you already have, was it FAPESP or some of the Brazilian groups helping fund, our funding can help you over the edge. So the conference program is actually quite popular. Yeah. Yeah. We can, and we have.
So that agreement that you mentioned with Brazil,
Yeah.
TV, whatever, is that a new one?
It's been off again, on again, and it had a cooling off period. There was one a long time ago. I don't know the full history, but for the last decade, I think it only got signed in around 2021, 2022. So I know the Army just processed an agreement, and I think the Navy's working on one. The Air Force is somehow not, it hasn't gone so well. We're still trying, and I'm trying to help. I said I can't, the RDT&E agreements are good for AFRL. AFOSR doesn't need the agreement because we can fund already, but we fund small dollar amounts, and the RDT&Es are typically more in the could be multi-million-dollar. But usually it's equal partnership of Brazil and the US. And I know ITA, the group in San Jose dos Campos, they've been very interested in trying to find support for projects like the EDASat, was one of their cube satellite developments. But it's been difficult. We're trying to find ways to help, but that's a good mechanism. I think Chile is the only other country in South America that has an RDT&E agreement with the US.
And we need those funds for visiting purposes.
Yes, it's not for ordinary conference attendance like pay you to go to a conference in the US. It's go to a part of the laboratory or the Air Force. Yeah, like if you wanted to go to the Space Vehicle Directed Energy group in Albuquerque, that would be an example. A lot of times what happens when you do that is you'll get with researchers and they'll say, oh yeah, we'd like to support, and you write a white paper, and it helps if they like the white paper because that helps us make a story with the transition, and it helps. Sometimes they'll provide support for funding. So the Windows on Science has been a very good program. So I would be very happy to help more Windows on Science applications.
Jesse just sent his regards.
Okay, I'll tell Jesse I said hi. I was very, very happy to see him get that big promotion. I worked with him since he was an undergraduate at UNM, of course.
Maybe you can mention that,
Oh, the ICEP. Yeah. Now, in Edel's case, that this is a good example. He has support from AFOSR on the U.S. side. If we had another, and there is a project I'm thinking of, a project in Brazil with our funding, which is also AFOSR. There is a supplemental grant that we can do. It's called ICEP, International Student Exchange Program. Now, in that program, we can send one or more Brazilian researchers to the U.S. for periods of time to do research at the U.S. institution. And so I think I want to mention that if you are in the process of preparing a grant or resubmitting a grant, it would be a very good idea to actually, you can put the hooks for it in the proposal. It has to be standalone. And this is more detail maybe than most people want to get into, but having the ICEP gives us a way to provide a little bit of additional funding for the student to come to the US, which I think is a very good idea. You should take advantage of. For me, it comes out of a different pot of money, so it's not in my budget. So it's like free money for me, and it helps. Yeah.
Okay, everybody's coming to Albuquerque.
Okay, we'll send lots of Windows on Science and ICEPs and
We can use your conference money
and we can,
for a workshop.
yeah. I heard Noronha is a nice place in Brazil, a little island where it would be a good place to have a conference. Or right here in Campinas is good too. Yeah, Campinas is good. Yeah. Well, y'all are set up. You have your own hotel and restaurant and everything. Mm-hmm. Yeah. Yep.
Thank you, Jim.
Thank you.
Thank you very much for today's presentation. And tomorrow we're going to start at 8 a.m. We have the presentation from Gelson Damiani, Renato Danino, and the others, Tânia Bueno também. So see you tomorrow. And this afternoon we have the visit to CPNM. Thank you very much and have a good afternoon.